Hello everyone. The title of this presentation is an overview of the role of solid-state transformer in smart grid. The presentation is based on the following outline: introduction, fundamentals of solid-state transformer in microgrid, functionalities of solid-state transformer in smart grid, and conclusion. The power quality of electrical grid is becoming vulnerable to transient due to continuous penetration of renewable energy resources and other distributed generation into the grid. Transforming the conventional grid into smart ones with improved communication and control have yielded significant improvement in terms of power quality and other ancillary functionalities. To facilitate this further, a solid-state transformer has been considered as the most aiding device for ensuring flexibility and intelligence, increased interconnection possibilities, improved reliability, voltage and current control, frequency stability, as well as power quality improvement in the smart grid. This paper therefore provides an overview of the basic functionalities of solid-state transformer in smart grid. Fundamentals of solid-state transformer. Figure 1 shows the block diagram of a typical three-stage solid-state transformer with control strategy. The control aspect consists of voltage balancing controller and a power balance controller. However, in the initial, one can see that the solid-state transformer consists of an AC-DC converter, a DC-DC converter, and a DC-AC converter. In the control block, we can see that it consists of a voltage balancing controller and a power balance controller. The voltage balancing controller is meant to regulate the high voltage DC link and also to control the power factor of the AC to DC converter, while the power balance controller is to regulate the low voltage DC link and also to control the flow of power between the two converters that form the DC-DC conversion states. SST in microgrid. Figure 2 shows the structure of microgrid integrating renewable energy resources, AC and DC load using both traditional line frequency transformer and modern solid-state transformer. In particular, Figure 2A is a case of traditional line frequency transformer which lacks the functionality of coordinated power routing, flexibility and control of active and reactive power, full drive-through capability, full isolation and limitation. However, the schematic shown in Figure 2B is a solid-state transformer-based approach which has the capability of addressing all the power quality issues that may arise, thereby providing flexibility and control of active and reactive power, provision of full drive-through capability, full isolation and limitation. Functionalities of solid-state transformer in smart grid. Number 1, voltage transformation with decreased volume and space. Similar to the conventional line frequency transformer that is meant specifically for voltage transformation, the solid-state transformer can achieve similar function with reduced voltage, volume, and space. This is possible because of the incorporation of the high-frequency transformer in the solid-state transformer circuit configuration. Figure 3 shows how the solid-state transformer replaces the conventional line frequency transformer in DC fast charger station, resulting in reduced volume and space. In the case of traditional fast DC charger configuration, the line frequency transformer is used to step down the high voltage AC, which is followed by AC-DC and DC-DC conversion stages. However, in the case of the SST-based DC fast charger configuration, the voltage step down is performed by high-frequency transformer, which results in a system with reduced size and volume, as well as higher efficiency. Number 2, microgrid integration. SST also facilitates smooth integration of both AC and DC microgrid with control flexibility and improved efficiency. Figure 4A and B show the role of solid-state transformer in AC and DC microgrid respectively. In both cases, different power converters are incorporated to condition the power to required forms within the required power quality that cannot be achieved with a conventional line frequency transformer. Number 3, reactive power compensation and harmonic filtering. Solid-state transformer, being an electronic device, can be configured to provide reactive power compensation and harmonic filtering as shown in Figure 5. This is particularly possible for a 3-stage solid-state transformer with DC link on both high voltage and low voltage sides. Number 4, grid integration of distributed renewable energy resources with improved power quality. In mitigating power quality issues such as voltage sag, voltage swell, voltage transient, and voltage flicker, a smart grid equipped with solid-state transformer can automatically adjust and maintain the system voltage and current to one having smooth sinusoidal waveform without the need of capacitor banks or other flexible alternating current transmission system known as spark devices such as static synchronous compensator known as STATCOM. Figure 6 shows how SST replaces the two line frequency transformers, STATCOM, capacitor bank, and some converters with enhanced power quality improvement in grid-connected wind farms. Figure 6A is a case of squirrel cage induction generator. Figure 6B is a case of WPED induction generator, while Figure 6C is a case involving direct driving synchronous generator. Other functionalities of solid-state transformer include disturbance and fault isolation, where SST can be used in smart grid, typically designed with fault right-through capability. It can also limit short-circuit fault current. Also, the provision of DC links disallows propagation of fault from one side of the system to another. It therefore provides smaller footprint, compactness, higher performance, fault tolerance, and improved power quality. Number 6, supply to both AC and DC low voltage ports. SST is a multi-terminal device equipped with different types of ports, AC and DC, single-phase and three-phase input and output, as well as special ports for the connection of sensitive loads. In the case of grid integration of renewable energy resources with solid-state transformer in smart grid, for example, wind farms can be connected to the AC port while solar photovoltaic panel can be connected to the DC ports. Number 7, extra flexibility and intelligence. With the help of sensors and communication and control, solid-state transformer makes smart grid flexible and intelligent to the extent that it can detect and address fault and disturbances so that they cannot be propagated to other sites. It offers reverse power flow. Furthermore, solid-state transformer can now deal with overload. Conclusion. This paper has investigated how solid-state transformer enhances smart grid to cater for intelligence and flexibility, control and communication, power quality improvement, disturbance and fault isolation, current limiting and short-circuit protection, as well as supply to both AC and DC low voltage port, among other things. It is concluded that solid-state transformer is an essential device in smart grid, particularly for the case involving large penetration of renewable energy resources and DGs and distributed generation to ensure system resiliency. Thus, with the help of solid-state transformer, smart grid can automatically control active and reactive power, harmonic filtering, as well as smooth integration of renewable energy resources and distributed generation. Thank you.